Thank you very much. I thought we weren't supposed to read bios, so I hope you not. The others don't get mad at me because my bio was read partially there. Yes, so I was asked to speak about urban forestry from the point of view of urban climate, which is of great interest to me. And I have been studying urban climate for many, many years now. I expect to do it the rest of my career, I hope. But I have to say outright that I really, to be fair, I've probably only been dabbling in the urban forestry side of this talk. So I will do my best to give you at least my perspective on the questions I've been trying to answer, and hopefully raise some thoughts that we could discuss as we go forward. I thought I'd start roughly my first half, maybe my first third of my talk, just giving you a few snapshots of what the heat island looks like in New York City. And again, I apologize, this is a very New York-centric view. I know Daniel Muth wanted us to put on a big hat and discuss the entire field, and I immediately realized that it was going to be impossible for me to do that. So I apologize again. It's going to be a New York-centric view because this is where I'm collecting my data, and cities obviously differ greatly with respect to their climate, rainfall, et cetera. So we have to bear that in mind. Even the questions on what kind of urban forestry we're considering was raised as well this morning. But anyway, let me just first give you a setup with a few snapshots of how the heat island looks. It's a very varied effect in different cities. We're convinced we have an extremely strong one in New York. I've been told that Tokyo is among the most powerful in the world, perhaps. But ours is no question that it's really strong and powerful. And these are just two views of it. One on the your left is the 2-meter air temperature from met stations that are distributed around the region. And on the right is a NASA Landsat remotely sensed map. The resolution here is really not as nice as on my screen. I apologize. Anyway, so these are two views of it. One taken early in the morning at 6 a.m. when that air temperature heat island is actually at its strongest, and then the other one taken at 10:30 in the morning. And I wanted to open with this because I also wanted to give you some of my experience dealing with policymakers and agencies and the kinds of questions and issues I deal with as a climate scientist and trying to talk about the subject. But one of the issues that always comes up that we take pains to distinguish is the difference between these two temperatures. Now, a lot of the folks here are well acquainted with these differences, but we always have to make them clear in terms of when we speak to policymakers and building owners, what have you, about what we're talking about. So on the left is, of course, meteorological stations or the 2-meter shelter height. And on the right is the radiometric skin temperature that Rao ST told us about from John's talk. And they're two very different things. One on the right is what you would literally feel if you put your hand down on that spot. These temperatures are searingly hot, vastly hotter, especially with dark surfaces, dry impervious surfaces, than air temperature readings. And so that's one thing. We take a lot of pains to sort those out. The other question about this is which is more important for a particular question. So for example, if you're concerned about building energy usage or human thermal comfort, which one of these is more important? Or if you're thinking about mitigating the heat island, which is more important? And I guess I'm just throwing this question out because it's something I've been thinking about as I was preparing for this talk. I think, in my opinion, when we talk about human thermal comfort and maybe building energy demand, I would think that air temperature may be a little more of an important parameter. This is the temperature that people are feeling as they move through. This is the temperature that's surrounding a building's envelope, the air that may be entrained within it. On the right, I would say the surface temperatures are perhaps more important when we talk about mitigating the heat island, because this is what's generating the hot, sensible heat. And when you talk about ways in which we can control the heat in the city, I think the first order priority, and there are going to be an array of technologies, but the first order priority is to try to control those surface temperatures and hopefully have an impact on air temperatures, et cetera. So I wanted to make that point as well. I was told this. Okay, so again, a few views of how it looks. That's one snapshot. This graph shows the Central Park weather station going back for the last century. That's the top curve on the upper figure, compared to 23 rural stations that are very far removed from the city, between 150 and 100 kilometers, a geographic ring. The reason we do that is we're trying to remove, first of all, we want to compare an urban station, Central Park, with rural stations, but we also want to be careful not to introduce longitudinal or latitudinal biases to the extent we can avoid that, so we use a concentric ring. In any event, this is annually average data. I think it's one of the easiest ways to look at the heat island, and you see the strength, the offset between Central Park and the surrounding rural average. One of the, and the lower graph, by the way, just shows the difference between those two plots. So you see in the early part of the century about a 2°C annual average, growing modestly to about 2.5 degrees. One of the things that intrigued us when we first generated this graph was how strong the heat island was back in 1900. If you look at archival photos of the city back then, a lot of the upper reaches of Manhattan certainly look like farmland to me. I'm sure many of you know the famous Dakota apartment buildings on 72nd Street, and I'm sure many of you know that it was named that because when it was built around 1900, it was considered to be so far north, it might as well be in the Dakotas. I assume most of you know that story. It's quite famous. In any event, it's very powerful, and the only explanation I can make of this is there was a huge population back then in 1900. In fact, the population of Manhattan Island was significantly larger than it is today, with a wave, a turn-of-century wave of immigration. And furthermore, this little bump back there intrigues me. It may be an artifact, I don't know, but it also actually that migration wave came and went. So it's very hard to see socioeconomic effects in temperature records, and it's intriguing me. That could be one, but I can't prove it yet. I need better quality assurance in some of the data. We've also been looking at this from the point of view of different weather stations around the city, not just Central Park, but I've been putting in weather stations. We've been using other private sources of weather stations. This is just a snapshot of how the heat island looks for these different weather stations in different boroughs and as hourly curves. So how much warmer at a particular hour on average is the city station compared to these rural stations that we're using by comparison. The point of this is just to show this, this characteristic U shape that's a very, very strong characteristic of the heat islands. It's primarily a nocturnal effect. This is another thing we need to make clear to the public. I think if you stop the average person in the street, ask them, when's the city sweltering compared to the rural areas, they would probably say the middle of the day, 1 o'clock. It's not that. In fact, in some ways, we're seeing some cool islands in the middle of the day that are actually cooler than the rural areas. And there's all sorts of interesting science that can come out of that. I have my own theories as to why. But anyway, this is a very strong effect. And this graph, I want to show just a quick histogram of what I'm calling the heat burden in the city, past, present, and future. So the histogram just shows the combination of the two sources of anthropogenic climate change, one urban heat, the other global warming, GW. And back in 1900, we assumed there was no global warming effect. We had about a 2 degrees Celsius urban heat island, like I just described. And on the bottom are some extreme temp statistics. We had about a week above 90 back then. Today, 2000, we add on an estimate about 1 degree global warming, about a ½ degree growth in urban heat island. And now we have about 14 days above 90. I think with the new climatology that we've been updating, I think we're even higher than that now, if you include the last decade. And statistics like the above 95, 3 to 4. Then what we do is we project this forward, and this is an important part of my talk. We project using mean changes in climate for the area, which in our spectrum of scenarios is about 3 degrees Celsius. And what we do, we generate new extremes with that. This is called downscaling, for those of you who are familiar with this field, where you try to take a climatology, say a projection for mean changes in climate, and try to downscale to get local changes in extreme events, which is really what a lot of agencies are interested in and what the public is interested in. In any event, you see this very strong jump in extremes. And at least to me as a climate scientist, I'm seeing increasing discussion about this, which is more important, the mean or the extremes? And the extremes are changing very rapidly. This is due, this is a highly nonlinear effect. And basically what we do is we take the Central Park record in this simple diagram for today, we warm it up by 3 degrees. And then the hot tails, we calculate how much above 90 and 95 are coming off those hot tails by moving it by those 3 degrees. And that's where you get a very strong ramp up from just say 3 to 4 days above 95 to 17 to 50, et cetera, above 95. So this is a very, very nonlinear effect that I'm seeing is coming up a lot in different fields of climate science. I don't know if it was appreciated enough in the early days when we were first making forecasts. But anyway, bear in mind that the Central Park climatology, because at my end of my talk, I want to make a point about that, becomes a really important part of those statistics. Now, in terms of tree work, we got started in our urban heat island research with funding from NYSERDA, the New York State Energy Research Development Authority. and Con Edison, our utility, and they funded us to do a modeling study of urban greening, including urban forestry and high albedo strategies. So we did this study. I'm not going to talk about it much, except to say that we considered lots of different vegetation strategies, including trees and open spaces, street trees, and then green roofs. We got started about that time on green roofing, which was new to a lot of us at the timing. And then we also consider high albedo surfaces, so raising the albedo of rooftops to a maximum extent possible, and then moderate increases in street level albedo, because those are much more challenging and not as acceptable to the public. In any event, just the point of this was to show that we actually got the most powerful cooling from a combined vegetation strategy where we just greened out the city dramatically. So I just wanted to make that point, that that's how we got started on our tree work, more or less, to speak. After that modeling work was over, I kind of decided that I needed to get out of the streets more myself, not doing any modeling, stop some modeling, and actually get out there and collect temperatures and, you know, go through alleys, get on rooftops, you know, measure temperatures on walls, et cetera. And I just showed this again. This is the Landsat map at 60 meters resolution. Extremely powerful tool, of course, I'm sure, as we all know, demonstrating amply the power of vegetation, Central Park showing up at the sea of cool temperatures. And then all these interesting little hot and cool spots that I spent, you know, many summers going to visit with students. It was a lot of fun work. I'd say students like doing this kind of work, taking them out with sensors and going and visiting hot spots and trying to figure out why some areas hot, why it's cool, why one's cool, et cetera. So we were asked, again, because I want to give you some of the flavor of the questions we were asked to do about when our study, our modeling study was done, we were asked by NYSERDA to answer a simple question: how much cooler is a street with trees on it than one without trees? So we spent a few summers trying to locate streets that were near each other that would fit the two criteria. That wasn't always easy. Then we would take some mobile sensors and go deploy with 2 teams simultaneously, making up our own protocols for how to do this, to tell you the truth. I would like some feedback for you as to what protocols should be followed for this, but we basically would deploy 2 teams with sensors that could measure both surface temperature and air temperature in 1 unit, and we would march every 5 paces. In New York City, the pavements have a 5-foot square size, I think, to measure distance to hydrants or dead bodies or whatever you want. But anyway, so that's a convenient marker. We'd march every 10 feet and then take the 2 readings, record them, et cetera. And this shows you 2 streets that fit the criteria in terms of being green and one that was less green. And generally, I just wanted to show you, we got a sort of an interesting scatter shot plot, which is similar to what Diane showed a little bit, but different x-axis. Here we're plotting the surface temperature versus the air temperature at a particular location. So what you're seeing for any dot, that was, we were standing somewhere, we took the surface reading, we took the air reading, and that dot shows you both those readings. So the good part of this was we did see always this positive correlation. So higher surface temperatures did in fact correlate with higher air temperatures. And in fact, in this particular case, these 2 streets, we did see overall the street that had more trees on it was cooler with both respect to surface and air temperatures than the one without the trees. And indeed, what's happening in this curve is on the hot end, we were out in the sun. So there were no trees or less trees, and so the sidewalk was getting quite hot, and the air, we were shading the air temperatures, by the way, always. And on the cool side, we were generally under trees. So this was a positive finding, but when we tried to, this was like our only case where we got a clear case where the green street was cooler than the non-green street. We went out many times and we could not, we'd see the opposite sometimes. And we concluded that there were so many factors when you move between streets, cars, building height, sunlight, winds, AC units, et cetera, that if you're not controlling for them, you're going to get very spurious results. The reason within a street, I think we got a nice positive correlation is because when you're within a street, I think you're controlling for a lot of those building variables, is what I concluded. Basically, the building stock's similar, the traffic, whatever. So that was the lesson I learned from that experiment. So the point was we were asked to prove this by NYSERDA, came back with mixed results, and so forth. We've also used fixed weather stations around the city to look at correlations between tracts of the city that are greened with urban forests and how they're correlating. So this shows 4 stations, 4 that I've installed around the city, 1 at Columbia, 1 in our Con Edison plant, which is sort of in the urban core, and then 2 that are kind of removed. One of them in north of the city in a very, very woodsy area of the Bronx, and another near Flushing, Queens, that was shown this morning as well, which is near the large botanical garden spaces. And indeed, you do see correlations between, large-scale urban forestry and the nocturnal greenhouse effect. So this, I guess, is a positive finding. Another experiment we were asked to do by our funders was they were very interested in what they called the spillover effect of the park cool islands. In other words, if you're living near a park, do you pick up a benefit in your building from lower air temperatures? Think about that. That's a very sensible question. I mean, if the park cooling only stays in the parks, how are we going to get the cooling onto the streets? So it's a good question. And in fact, the how parks cool is an important urban climate question as well. I have found this this has been challenging in terms of showing how they cool off. I did want to show this early graph of a march through the park, a traverse that we did through Central Park at nighttime. At nighttime, I found during the day it's much more complicated to see what's going on. But we started on the west at 9 o'clock, started marching towards the park, the boundary shown on that vertical line there. It's cooling off. However, there's nocturnal cooling going on at the same time. So we're unable to sort out whether or not approaching the park was all nocturnal cooling or partly nocturnal cooling and the park cool effect or all the park cool effect. So I haven't been able to disentangle that question. We entered the park, sort of marched through it, and then as we exited the park, you see this very strong warming was taking place, which is a very, very clear urban heat island signal, because obviously nocturnal cooling was continuing as we left the park, but we see that we started leaving into the streets, and they started getting hotter in defiance of the nocturnal cooling. And I think my talk's really short because I'm almost near my end. Maybe I'm talking too fast, but which brings me back to the Central Park Station, because those of you who know it and have been there, it's near Belvedere Castle. It's a big tourist site. It's a very heavily forested area, really, really wooded. And so this raises the question to me, unless you live in Belvedere Castle, nobody does, is that station a good representation of what the climate's going to be in the streets or where people are living and working? So this, to me, I think is an important urban heat island question I'd like to answer better, because again, I'm reminding you, we use that Central Park climatology to generate all the statistics for days above 95 and days above 100. What will happen? What if the climate in these other locations in the streets where people are living and they're playing and working and walking is a degree or two warmer? That's going to generate the statistics up much more. In other words, what we're estimating for days above 90 may really be much lower than what people may actually feel where they're living and working. So I'm very interested in this question now of getting high quality air temperature data. Now, that's not easy. I mean, the Central Park Station is probably one of the best, highest quality air thermometers in the world. Trying to compare it with other cheaper stations is not going to be easy. So I'm still trying to think of ways to do this well. But my point is, I don't know, I'm starting to think about different levels of urban warming with respect to urban forestry. So we can start with the parks as the best urban forest examples. Are they the coolest? And then moving on to well-green streets and neighborhoods, are they warmer but still cooler than other locations? Then poorly green streets and neighborhoods, and then poorly green buildings and residences. I mean, I think understanding the biases in using stations within parks or at airports, I would say, is an important thing for understanding these extremes that people are really going to feel and are going to get them motivated to do something about. So really, in closing, I was asked to answer these three questions. What's the current state of the science in your respective disciplines, and what are some examples of well-documented conclusions and metrics? So I think the heat island characteristics are well-documented on large and larger space and time scales. I think urban green infrastructure and albedo strategies are clearly understood as first-order UHI mitigation methods. There are going to be others as we reduce anthropogenic heat, in cities. That's going to be another approach, et cetera. In terms of what are remaining challenges and questions and what additional science and observations are required, I would say we need better tools and methods for understanding the small-scale microclimates and benefits of urban green infrastructure. better modeling capabilities to study large-scale greening and albedo strategies to determine overall long-term benefits vis-a-vis global warming. So, we're being asked to answer these questions like, what happens if, how much cooler will the city be if we just, maxed out on our green and albedo strategies? And, I don't think we can answer those questions without modeling them now, because it's going to take time to implement them. So I think those become, very important modeling questions and doing more of those kinds of greening scenarios, like I think Jonathan was starting to do in the talk before lunch. Yeah, because I think the jury's still out. I have to be honest, I don't really know how much we can cool off New York. I mean, I like to believe we can do a great job on it, but I'm not confident about saying a number yet. And I think we need to answer that. So then finally, I think we need to understand the biases in weather stations located in parks and airports and how these may be affecting the statistics, and even pre-SIP and CSO events that are happening around the city. So how do you do on time? Good? Okay. That's it for me. Thanks.
So we have time for questions, and please come up to a mic to voice your questions so that we can have that for the record.
Is this a question just for me or for the panel?
So you can go sit down.
So no questions.
All right. False alarm, my fault. Okay, so our next speaker is Doug Tallamy, who is professor and chair of the Department of Horticulture at Cornell University. And he focuses on the use of ecosystem functions, using plants to restore ecosystem functions to cities and other landscapes that have been impacted by humans. And what's especially important is that he has an interdisciplinary approach, making use of ecology, atmospheric science, soil science, and hydrology. Look forward to it.